So again, welcome to the webinar series, the first of this year of the Committee on International Relations in Statistics of the American Statistical Association. I'm joined here by Carolina Franco from NORC and Donna Lalonde from the ASA. We are the main organizers of this webinar. And it's my great pleasure to introduce Dr. Tamara Broderick, who is an associate professor with tenure in the Department of Electrical Engineering and Computer Science at MIT. If I list all the awards that Tamara has already received, we would spend the whole 1 hour and a half. So I'll just summarize some of them. Her main focus of research is on fast, easy to use and reliable methods for quantifying uncertainty and robustness. She has been awarded the Presidential Early Career Award for Scientists and Engineers in 2025, the designation as an IMS Fellow in 2024, selection to the COPS Leadership Academy in 2021, and she was the Susie Bayari invited lecturer of the International Society for Bayesian Analysis, and she won the Savage Award, which is a prestigious PhD thesis award of the International Society for Bayesian Analysis. Tamara is a very active member of ISBA, and it's my great pleasure to introduce her today. She's going to talk about Gaussian process, about questions. If you do have questions, please place them on the Q&A. Tamara will be monitoring, and I will be here helping her as well. And yes, the floor is yours, Tamara. Please go ahead.
Great. Thank you so much. Thanks for the extremely kind introduction. Thanks to everybody for coming from so many places today. I really appreciate it. As we said today, I'm going to be talking about Gaussian processes for regression. My understanding is that all of my slides and code will be provided on the webinar webpage later. I'll also be putting them on my own personal webpage, which you can find here. So there should be plenty of places to find all of this information afterwards. I'll be doing some demos, and that's where the code will come in. So before I go into details about Gaussian processes for regression, I'm going to just talk at a little bit of a high level about, what motivates us to consider Gaussian processes for regression. And before I go on, I should have asked this earlier. Would anybody on the panelist webinar committee be so kind as to leave your camera on? I just, for my own presentation, it's a little bit easier. Thank you so much. Really appreciate it. Great. Okay, let's dive in. So again, before we get into technical details, let's talk about why are we thinking about Gaussian processes. At a very high level, we often want to estimate some continuous outcome as a function of certain inputs. This will often be called prediction when we're talking about regression. I think this will be helpful to illustrate with some really concrete examples, which I'm going to get into on this slide and the next one. And the thing we're going to see in these examples is that Gaussian processes are really good at certain types of regression problems. So here's one very concrete example that oceanographers are interested in. They'd like to predict the ocean current. You can think of that as a velocity vector field. So what's the direction that the ocean's moving in at particular places in space and time? So that is to say latitude, longitude, and time. And so, what are they using to make these predictions? They're using data that come from buoys. And so, scientists take these buoys, they go out into the ocean, they put them into the ocean, they move around with the current, and we get observations from those buoys. But those buoys are necessarily sparse. They're only at particular places in time, and we'd like to predict the ocean current away from them. In particular, we'd like to estimate the current. Now, I use this word predict, and I do want to just emphasize that in this area, and especially in sort of machine learning more broadly and statistics more broadly, we'll often use the word predict to say we want to know the value at another, in this case, location in space and time. Some people think of predict as saying forward in time. Here, that doesn't have to be the case. We could be interested in the value within times we've already seen, and we might still use the word predict. So I'm just putting that wording choice out there. Okay, so I said that regression was we want to estimate or predict some outcome as a function of some inputs, some output as a function of some inputs. Here, the inputs are space and time, and we'd like to say if I have a new space and time where I don't have a buoy observation, can I predict the ocean current? Can I estimate the ocean current at that space and time? Now, There's a lot of problems that have this regression format where you're trying to say, hey, I have some inputs, I want to predict some outputs. What are challenges that are specific to this problem? One, the data is very sparse. We don't have buoys nearby everywhere we would like to predict the current. So that's definitely a challenge. It's very expensive to collect the data. It's not like, oh yeah, we don't have this data, that's fine. We'll just go out and with no time at all, have a ton more data and be able to fill in everything. Here it's very expensive. And so we might not be in a situation to just get more data out of nowhere. The observed data is definitely not going to be on a nice grid. It's going to be where these buoys happen to travel. An additional challenge is that we can just know from our own intuition that the ocean current is going to vary in some highly nonlinear way with latitude and longitude and with time. So we can't just apply a linear regression or even a polynomial regression. It might be rough here. But we do know some things about the problem. We know that there's probably a certain amount of smoothness, some smooth variation. If I'm very close in space, I expect the current to be very close to what it was at other points in space. If I'm very close in time, I expect the current to be close to what it was at other points in time. And finally, we want uncertainty quantification. We'd like to say not just what's our best guess of the current away from our observed data, but how certain are we of that guess? And it's going to turn out that basically these challenges are exactly cases where we would like to apply Gaussian processes as a particular form of regression methodology. Okay, let me give one more example, 1.5 more examples before we dive into what we're actually going to do in terms of methodology. This example is of a so-called surrogate model in engineering. Basically, the idea is, hey, it's really, really expensive to, do the experiments we'd like to do, and so we're going to have a surrogate model for what happens instead. Here, engineers are interested in the lift force of a rocket booster. So this could be NASA in the United States, somebody who's interested in these boosters that could be used as part of some exploration of space. Well, the lift force could vary as a function of various inputs. These could be the function of the speed at reentry. They could be the angle of attack. They could be the side slip angle. These are things that when we change them, we might expect the lift force to vary. And so we could think of them as inputs and the lift force as outputs. Now, this is sort of an interesting situation. Of course, it's super expensive for scientists to run actual experiments, build an actual rocket booster. But fascinatingly, even running simulations is very expensive here. So you can run an expensive simulation to say, hey, if I choose my speed at reentry, my angle of attack, my side slip angle, what's my lift force for this rocket booster? But it's so expensive that I don't want to just fill in everywhere, every possible input with an output with it. And this is a case where I might use a surrogate model to try to predict at other places, what's the value of the lift force as a function of these inputs. And maybe, how well do I know it too? Maybe there are cases where it really is worthwhile to spend the time on that full expensive computer simulation. Okay, so we're seeing this motif again. I have this very sparse data, sparse in this case just because it's so expensive to gather. In this case, expensive in time as well as computing resources. It's not necessarily on a grid. We could, in this case, maybe choose to have some grid observations, but we don't have to. The output definitely can have a nonlinear relationship to the inputs and no particular polynomial relationship either. And we want uncertainty quantification. We know what are the areas where we don't know what's going on, and we'd like to be able to say more about it. Maybe we'd like to run more experiments there. I also want to highlight something that was true of the oceanographic model as well as this model, that the number of inputs is relatively low dimensional. What I mean by that is there's just a handful of inputs. So in the oceanographic model, the inputs were latitude, longitude, and time. So that's 3. In this case, we're looking at speed at reentry, angle of attack, and side slip angle. That's 3. So that's going to be another thing that is a common place where people are using Gaussian processes very effectively, where this is a useful regression application. Okay, finally, one more example. This will be a little bit shorter, and then we'll get into the details of Gaussian processes. So you can think of Gaussian processes as a method in machine learning, but of course, there's a lot of other regression and other methods in machine learning. This could be things like we're interested in deep learning methods, or maybe I'm interested in modern LLMs, large language models. Basically, all these different methods that exist in machine learning have tuning parameters associated with them. And so something that people often use Gaussian processes for is they want to predict for various settings of the tuning parameters what's going to be the performance of the machine learning method, something like regression accuracy. And then once I have this surrogate model for how that behaves, I might even optimize it. I might say, what are my tuning parameters from a machine learning method, like my deep learning method, that are going to give me the best performance? Somebody asked in the Q&A, will the presentation be posted somewhere? Thanks to Alex for typing in the answer as well. And I just want to remind people that it will all be posted on the webinar webpage and also on my webpage later as well. Great, thanks. Okay, so let's start digging into Gaussian processes. Hopefully at this point, we're really motivated to understand what they're doing. And so what I'm going to be doing in the rest of our time together is first just sort of briefly overviewing that Gaussian processes are fundamentally a Bayesian modeling approach. And so what does that mean for how we're going to build them up? In particular, we're going to start by defining a model, the Gaussian process model. It turns out Gaussian processes are actually extremely wide in terms of a concept. They can really mean a lot of different things, but a really popular version, especially if you use any sort of standard software package, is going to use this thing called the squared exponential kernel. You can think of that as just a type of Gaussian process. And so we're definitely going to focus on that today. Now, once we have a model, we can do inference. We can use Gaussian processes to predict, as we said, predict at other times and locations, and to do uncertainty quantification. So these are things that we might want to do. And so, we'll talk about how to do that once we have the Gaussian process model. My goal in all of this is hopefully by having you understand the mechanism by which Gaussian processes work, you have the ability to think through what are the benefits and pitfalls of Gaussian processes. What do they do well? What do they not do well? I think this is a really important point with any method in data analysis whatsoever. There are going to be some things it does well and some things it doesn't do well. There is no one-size-fits-all method. And so really understanding those, I think, is just really important in general. Okay, so with that all being said, let's dive in to taking this Bayesian approach and then what is a Gaussian process. So what do I mean by a Bayesian approach? Well, at a super high level, what we want to do is we want to say something about what do we know about a set of unknowns given some observed data. So we're going to see some data. We assume we have access to some data, like, we have these buoys in the ocean, or maybe we have some air sensors that tell us about some pollution level, and we want to predict pollution levels at other locations and times. And we want to say, basically, given the actual observed data, what do we know about the underlying function? And so here's just a little cartoon of what we're going to be building up. We're going to imagine we have access to data. So maybe think of this as a plot of air pollution as a function of latitude. We're going to imagine that we have some air sensor data, but what we really want to do is we want to predict at other locations, places where we didn't have the air sensor data. And we don't only want to predict, so you can think of this green line as our best guess given our observed data. We also want uncertainty quantification. We want some element of saying, hey, how certain are we? What's something like a 95% interval for where we think the air pollution values might be outside of the observed data? So this is the kind of thing that we're going to try to build up to. So again, we're thinking of X here as the input and Y as the output. Now, the Bayesian approach is to say, hey, what I want to know is some distribution over the unknowns. In this case, the unknown is, the air pollution at other locations, given the data I've observed. And Bayes' theorem tells us we can flip that around. And if we were able to make a model for the unknowns and for generating fake data given the unknowns, then we could do inference. So you can think of this as a statistical model that can generate functions and data of interest. This is just going to be fake data. And then Bayes' rule is going to let us turn that around and say something about what do we know given the actual data we see. So the first thing that we're going to do together is we're going to try to visualize, we're going to try to create smooth functions. So you can think of this orange, green, and blue function as the smooth functions to try to generate. And once we have these functions, we can make data points on them by saying, what are the X's that we care about in the data? Okay, so let's try to generate these functions together. And to do that, we're going to start by briefly reviewing and making sure that we have really, readily available to us a lot of intuition about just straightforward Gaussian distributions. So let's start with a multivariate Gaussian distribution. In particular, let's start with the simplest multivariate Gaussian distribution that we can have, m equals to a bivariate Gaussian. So that is to say, when I say m is equal to 2, I mean we're going to make two draws, y1 and y2, from a bivariate Gaussian. So a bivariate Gaussian is fully described by its mean and its covariance. So the mean here is going to be a too long vector. Let's just assume the mean is 0 in both dimensions. The covariance matrix is going to be some variance, sigma squared, times the correlation matrix. That's 1 on the diagonal and has some correlation rho between the 2 points. And so this is what a draw from this bivariate Gaussian is going to look like. We're going to have a draw for y1 and a draw for y2. And then the thing that we're going to do, so hopefully up to this point, you're familiar with bivariate Gaussians, you've seen bivariate Gaussians before. What you might not have seen is taking bivariate Gaussians and putting them at particular locations. So what we're going to do is we're going to say, suppose I had two locations of interest. Like I'm interested in the air pollution value at Boston and in Detroit. I'm going to take my bivariate Gaussian values and I'm going to put them at the corresponding location. So y1 is going to go at location x1 and y2 is going to go at location x2. And I want to emphasize that x1 and x2 do not have to be in order in the x space. It could be that x1 comes farther on in x values than x2. It has a larger x value, in which case y1 would be to the right of y2. Okay, so all we're doing here, there's nothing too special, is if I had a vector of x values, I could put my y values at those x values. Now here's the next thing we're going to do. Now we're going to let the distribution of the y's depend on the x's. What if we let the correlation in particular between the two y values depend on the x's? And the thing we're going to do is we're going to say that the correlation depends on the distance between the x's. If the x's are extremely close to each other, we're going to say that correlation goes to 1. And if the x's are extremely far from each other, we're going to say the correlation goes to 0. That is to say, the y values are basically independent. So when the correlation is 1, the y values have almost the exact same value. When the correlation is 0, the y values become basically independent. Okay, so with all of this in mind, let's go ahead and look at our first demo today. So we're going to have a variety of demos. I'll also be sharing the code as well as the slides today. Okay, great. So we're looking at our code together. And what I'm doing here is I'm making exactly the draws I said before. I've got y1 at location x1, that's 0. I have y2 at location x2, that's 3 in this case. And these are just draws with a sigma squared value of 1. And so the reason I have this 2 to negative 2 here is that's a 95% interval for this particular value. And because I've chosen these to be far apart in x's, they have essentially independent draws. Sometimes they might be close to each other, sometimes they might not, but that's just randomness. These are just two independent Gaussian draws. Okay, so I could imagine doing 3 sets of y1 and y2. And you can see the ordering between these 3 sets really doesn't matter because essentially these are just independent Gaussian draws at the 2 locations. Now the thing I'm going to do next is I'm going to set the location of the second point. So here it was 3. I'm going to set it to be 0.05. That is, it's going to be right next to the first set of points. If I do that, and this is a real question that I'm asking you, and I'd love for people to respond in the chat if you feel comfortable. You can also respond privately to me in the chat. I can see everything in the chat, so you can either respond publicly or privately. These are all fine. What do you think is going to happen? So right now it looks like I have these 2 independent set of draws here. But what's the blue dot going to look like relative to this blue dot when I make x be right next to this x? And remember, we're saying the correlation is going to be very, very near 1 between these points. Can anybody in the chat say, what do they think, where do you think this blue dot is going to be relative to this blue dot when the x is very nearby? Great. Sweet. Awesome. These are fantastic answers. It's going to look a lot closer. It's going to look like it's almost the exact same value. Wonderful. These are all really, really wonderful answers that are in the chat. Okay, we've all got a hypothesis. Sounds like we're on the same page. Let's try it out. Yep, this is what we're seeing. So now we're making all these draws, y1 and y2. We're doing it 3 separate times. And we can see that every time the values are just extremely close. The blue dots are close to the blue dots. The orange triangles are close to the orange triangles. The green X's are close to the green X's. So when we have that correlation very high, our values are very close. Okay, perfect. We're still building up to Gaussian processes. Let's go back to the slides, and then we'll come back here. Okay, great. So we saw a demo. We saw what this looks like. Now we're going to extend this just a little bit. So instead of having a 2 long Gaussian, we're going to have an m long Gaussian where m could be larger than 2. 2 will just be a special case. So we're going to have m locations. Before we had 2 locations, by which I mean the x values, that horizontal axis. They don't have to be in order. It could just be any m real valued locations. And we're going to use this superscript to define which point we're on in the x space. Again, that's that horizontal axis. And then we're going to generate our capital M y values, the vertical axis, according to a normal distribution. And we need to find its mean and its variance. There was a question in the chat, what about location as well as time? So right now I'm talking about the x's as though they're locations, like they're a latitude. You could also think of them as time. And so in reality, when people use Gaussian processes, they don't just use a single input dimension like I'm using, they use multiple input dimensions. And so you could have x sub 1 be time, x sub 2 be latitude, x sub 3 be longitude. And so you can have both time and physical location in the same model. I'm going to keep things to 1 dimension here just because it's easy to draw, but I actually think it's really important to be thinking about how things will change as you get into 2 and more dimensions. So that's definitely a very reasonable thing to be thinking about. Great. Okay, so let's go back to our building up our M draws now instead of just 2 draws. So we're going to take the mean again to be all zeros. So last time we took our normal mean to be 0 and 0. Now it's just an M long 0 vector. And we're going to take the correlation matrix to be a variance, so sigma squared just like before. And we have a correlation just like before that is some function of the distance between any 2 x values. Here's the correlation that we're going to try. So this is my proposed function. This is the correlation when I have some distance delta between 2 x values. This is another one for the chat. Can anybody tell me in the chat what, if I take this particular rho function, what rho of 0 is equal to? Okay, again, looking great in the chat. It's 1. So we can just see this from the exponential function applied to -1/2 0. That's just the exponential function of 0. That's 1. But let's also think, hey, this is what we wanted before. So remember in the last slide, we said we wanted it to be the case that when 2 points got arbitrarily close, that their correlation went to 1. And so that's the same thing is happening here. When 2 points get really close, their correlation is 1. Okay, here's the next question for the chat. If I increase the distance between 2 points, does the correlation increase or decrease? There's only 2 possible answers, increase or decrease. As I increase the distance between 2 points, does the correlation increase or decrease? Awesome. Yeah, amazing answers. It decreases. And again, we can just check the exponential function in this case for that as delta gets larger, the input to the exponential gets smaller, and then the exponential of that input gets smaller. And in fact, we can check how much does it decrease? Can anybody say, if I take this distance between 2 points to be arbitrarily large, what does this correlation, what value does it go to? Awesome, amazing. Fantastic engagement here in the chat. It's going to go close to 0. So as lambda, as delta, as this distance between points gets larger and larger, this correlation between points is going to go to 0. And again, this is exactly what we said on the previous slide we wanted. We wanted when 2 points are really close to each other in x, We want their correlation in y to be near 1. Essentially, when they're close in x, they're close in y. And when they're far in x, we want them to not really have anything to do with each other anymore. They're going to be essentially independent. Their correlation is going to be 0. So our previous example is really just the special case of this when m equals 2, and now m is just larger, and it's the same deal. And so let's go ahead and check out what this looks like visually. Okay, so we're back to our demo. We saw this demo from before, and now we're going to look at 3 points. So I have, on this end, I have my x1 and x2 at 0 and 0.05, and my x3 is at 3. And so we're seeing, try to move this down a little bit more, we're seeing that the 2 points with the very close x's have very close y's. Same here with the green x's. And then the 1 point with the very far x has a very, independent y. Could be close, it could be far. It's just independent of those other points. So we can make a bunch of draws like this. I'm just making different draws from the same process, from the same multivariate normal. It's m, capital M here is just equal to 3. So these points are close to each other. And this point is just independent from those. The y value at this x is just independent. Okay, so now the next thing I'm going to do is instead of having 1 point over here and 2 points over here, I'm going to have 50 points, 50 points, and they're just going to be evenly distributed across this whole space. So totally the same idea. I've chosen my x's now to just be evenly distributed across the space. I can choose whatever x's I want. I've chosen these x's. And we're seeing, again, if I look, for instance, at this curve of orange triangles, that if 2 points are very nearby to each other in x, in the inputs, then they're very nearby to each other in y in the outputs because the correlation is nearly 1. And if I have 2 points that are very far from each other in x, so this one versus this one in the inputs, then they're essentially independent in the outputs. But if I look pairwise along the way, all these 2 points are close to the ones next to them, and so I end up getting what looks to be basically a smooth curve. In fact, I could make this look as smooth as I want by just increasing the number of points. So here I've done 50 points across the inputs. What if I just did 200? I can just make this look like it's this perfectly smooth curve. And remember, we said our goal going into this was to come up with a model to generate smooth curves that could be nonlinear, that could have the properties of a function that we'd like to learn in reality, and we've done that now. We've come up with this way to generate smooth curves just by using simple multivariate Gaussian distributions. Now I want to note here, I have this signal standard deviation here that I can change. So for instance, if I set that to 1, so this was the sigma squared before, then any single one of these points, it's Gaussian distributed with standard deviation equal to 1. And so the reason I have this gray region here is that the plus or minus 2 standard deviation region for any single point is -2 to 2, because it has a mean 0 and a standard deviation of 1 for any single point. And then, of course, as soon as we look at a few points, they have all kinds of interesting correlations as we've described. Okay, awesome. So let's go back to the slides, but basically, we've done it. We've done this thing that we had said was our first goal, which was to draw random functions, to have a model to draw random smooth functions. And so we've essentially done that from a type of Gaussian process now. And I'm just going to take a moment to step back and say more precisely what is a Gaussian process now that we've seen this example. Okay, a Gaussian process is any collection of random variables, any finite number of which have a joint Gaussian distribution. So an example of this is the function. I could have a function that's, the various y values that we saw before. The index is just the input, x. Now, one thing that's different on this slide from the previous slides is x is bold, and I'm using that to indicate that x could be a vector. So as we said sort of before, based on one of the questions that came up, X could be something like a vector that is both time and latitude and longitude, in which case it would be a 3-long vector. But it's easy for my drawings to make it one-dimensional. And so in the visualizations we've seen, there's been one dimension. You can think of that as space. You can think of that as time, but it'll only be one of those dimensions at a time. Now, a Gaussian process is a way to randomly draw these functions, but how do we randomly draw essentially these multivariate Gaussians? Well, they're specified by a mean function and a covariance function. And this basically just tells us how to get the mean and the covariance for the multivariate Gaussian. Because remember, we had a mean vector before and a covariance matrix. And in particular, the mean function tells us that any element of a mean vector, like if I want the mean at a particular location X, this is just telling me the expectation of F. It's the mean at that location. The covariance function is likewise telling us the covariance now between 2 locations. So for instance, we said before, if I have a location that's nearby another location, this covariance in general is going to be the variance times the correlation. And if the 2 locations are nearby, the correlation will be near 1. If the 2 locations are far apart, then we might choose the correlation to be 0. That's what we did in our example. Technically speaking, for very broad Gaussian processes, you could choose something else. X could actually be just about anything. It doesn't even have to be a vector, but we're just going to assume in this tutorial it's a real vector. And we're pretty much going to focus on the case where it's just one-dimensional, not that you have to. It's very common, again, to use 2- or 3-dimensional or a bit more higher dimensional stuff. Okay, we've been using the mean function equal to 0. That's an extremely common default, especially in software, but it's worth noting that it is technically something you specify about a Gaussian process. What does its mean? Also, technically, the covariance function is something you specify. We've been using a particular covariance function known as the squared exponential or radial basis function, RBF. So far, we used a very slightly different version of this. The slight difference is that we weren't thinking of X as a vector before. We were thinking of it as one-dimensional. So we just used the difference between X and X prime for the distance between 2 points. But we could have a more general conception of distance in this as well. And that would still be part of this squared exponential covariance function. In fact, there are even more things you can change about the squared exponential covariance function depending on time. We'll get into some of them today. If not, I'll point you to places where you can learn more about them. But this is the type of covariance function that is often used in software, and it's the one that we're going to focus on today. And I'm basically just letting you know that there are other things that you can do in a Gaussian process, not just this one. We're also assuming for the moment that data is observed without noise. That is to say, for instance, I'm doing a computer experiment and oh man, I don't want to run my whole simulator for lift as a function of the various input variables. And so, because I'm running a computer simulation, I imagine I get the same output every time that I run it. And it doesn't matter, that I have the same inputs every time, I just always get the same output. But there are cases where I might also have noise. So for instance, if I truly was measuring air pollution, there might be observation noise on my air pollution monitor, and then I would want to include noise. Again, if we have time, we'll get to that, but right now we're not assuming that. We're just assuming we do not have noise. Okay, so let's see what this looks like in terms of generating data by going back to our demo. So remember, right now we're still in this stage because you were thinking about doing Bayesian inference. We're still in the stage of generating fake data. We haven't yet said, hey, we have real data, and we're going to try to learn something about it. And so let's think about what does that look like to generate fake data. And so what we're doing here is first, I'm doing exactly what I did on the previous slides to generate this blue dashed line. That is to say, I'm drawing a multivariate Gaussian, but there are so many points that I'm choosing along the input that it looks like this smooth line. But the reality is it's really just a finite number of points from a multivariate Gaussian, and that's how I'm getting this smooth blue line. And so I could just draw a whole bunch of these. These are all just draws from my Gaussian process. It's giving me this random function. Okay, now let's say I'm actually going to generate some fake data, some simulated data. Well, to do that, I'm going to have to specify where am I going to make my observations. In this case, I chose them to be at 0, 0.05, 0.7, and 3. So 0, 0.05, 0.7, and 3. Those are the inputs where I'm going to choose to have an observation. And so then I have these 4 data points because I just look at the function value at those inputs. And so after I've done this, I can just ignore the underlying value and I can say, hey, my data set is just those 4 points. So we've generated a fake data set from a Gaussian process here. And the next thing we're going to want to do together is we're going to want to learn how to do inference once we have a collection of data. Okay. So remember this high-level Bayesian idea. We said if we had the ability to generate fake data, if we could come up with a model for smooth functions and then data points on those functions, then we could flip that around using the Bayesian machinery and use that to get inference when we don't know the function, but we do know the data, which is real life. In real life, you know the data, but you don't know the function, and you're trying to learn that direction. And so that's what we're going to do next, is we're going to say, supposing I have data, how could I learn about the values of the known function? How could I get uncertainty quantification about this unknown function at other locations, at other times? Okay, we're going to start introducing a little notation here. We're going to let capital X collect capital N training data points. So that is to say, in real life, you really have observed capital N points. Like I put my air sensors out in the world, I observed capital N air sensor observations. I got that. That's how many data points I have. And now I want to learn what's going to happen at other locations. And so capital N is the number of data points. And in general, capital D is going to be the dimension of each one of those points. So for instance, if I know the latitude, the longitude, and the time of those points, then capital D is going to be 3. And my observation will be the air sensor value, that'll be Y. But X will be the time, the latitude, and the longitude. Now remember, just a moment ago, when we were generating this smooth function, we generated it capital M points. But we're going to do the same thing now in terms of prediction. We're going to say, hey, we're interested, given some data, in the predictive values of our smooth function at the air pollution at other locations and times. And so these are going to be the places we're interested in, maybe to draw a curve, in which case capital M will be very large just to draw that curve like we just did. Or it could be some particular points we're interested in. That's totally fine too. But this will be a capital M by capital D matrix X prime, the points where we're interested in making a prediction. This is where, again, we want to evaluate the function. We can think of this as being one data set in some sense. It's just that we only have observations at X, not at X prime. We only know the function at X, not at prime. But if we think of it as one set of X's, then we have 1 up to capital N training points, and then N plus 1 up to N plus M test points. And so from that perspective, I could think of, hey, I've got my function evaluation at my X training points, and I've got my function evaluation at my X prime test points. And that's just a big old set. Oh my gosh. Thank you so much for pointing this out. I did think that I was on my slides. And so I'm really glad that somebody pointed out in the chat that that's not the case. Yes, great. Okay, hopefully we're all set now. Thanks so much to the folks in the chat. Great. So what we have here, so let me go back over this. We have capital X. We have capital N training data points. Each one of them has size D. So we have X in an N by D matrix. We have our capital M test points where we want to be evaluating this. We want to be saying, hey, here's where we're doing our prediction. And so we can think of this as, hey, we know the value of F at capital N points. We want to know the value of F at these capital M points. Okay. And so now my question for you is, on the previous slide, we said that we had this model, this Gaussian process model, and that our observations F could be thought of as having some distribution, some joint distribution. And I'm wondering if you remember, what is that joint distribution? Is it a gamma distribution? Is it a Poisson distribution? What common distribution is that? If anybody's up for saying this in the chat. Hopefully you can all see my slides now. Awesome. I really appreciate everybody who's so active in the chat. This is really wonderful. This is our model. It's, I mean, you know, hopefully this felt like a relatively straightforward question. It's called a Gaussian process because everything is Gaussian. When in doubt, the answer is the distribution is Gaussian, and that's the case here. So yeah, there are some points that we think of as training points and some points that we think of as test points. But the fundamental idea of the Gaussian process is that everything is jointly Gaussian. In particular, the observations F are jointly Gaussian. Now, we made a particular choice though. So we said in general in a Gaussian process, you can specify a mean function, but we made a particular choice of mean function. Does anybody remember what that choice was? We weren't going to use just any mean function. We were going to choose some particular mean function. Amazing memory. Fantastic. The particular choice that we chose for the mean function, and everybody is just absolutely nailing this in the chat, is the all zero function. Fantastic. Yeah, great. Wonderful. So basically what we're saying is, hey, in general, I could have a Gaussian process with some arbitrary mean function, but we're going to choose this particular mean function that the mean is zero. A priori, we think the mean is zero. Now, of course, after we see some data, things are going to change, but a priori, before we've seen any data, the mean is zero. Now, I just want to really emphasize what are the dimensions here, because we have a total of n dimensions from the training data points. We have capital M dimensions from the testing data points. And so together, we're putting a zero mean over n plus m total things. Okay, next for Gaussian, there's one more thing that we have to specify, and that's the covariance matrix. And I'm just going to say, hey, the covariance matrix, the covariance we said between any 2 points is the covariance function applied to those 2 points. And so we're going to introduce this new notation, capital K, of capital X and capital X prime. And that's basically the matrix for all the covariances between these points. Exactly. Little k is the kernel. It's the kernel function. So we're applying the kernel function, and we're applying it at each pair of points to get the covariance matrix. And so here we can write out our covariance matrix as having these various parts. There's the covariance matrix between the training data and the training data. There's a covariance matrix between the testing data and the testing data. There's a covariance matrix between the training and the testing data. And this whole thing we can check has the correct appropriate dimensions, n plus m times n plus m. Okay. Can anybody happen to remember, either from your own knowledge or because you can make a really good educated guess, what type of distribution f of x prime conditional on f of x is going to be? So the type of answer I'm looking for, again, is something like, is it a Poisson? Is it a gamma? Is it a Wishart distribution? What type of distribution is it? This is either something you could know from facts about multivariate Gaussians using the formula above, or it could be something that you make a good guess on. Awesome. Yeah, great. Again, if you just made a guess that everything was Gaussian, it's probably a good guess right now. I mean, again, they're called Gaussian processes for a reason, not just because Gaussians are a fun distribution that everybody loves, but because everything works out so nicely in Gaussian processes to be Gaussian. And so indeed, it is also going to be the case that f of x prime conditional on f of x. So what does this mean? This means, what does the function look like given that we've observed some of its points, the training points? That, in fact, is also a multivariate Gaussian. Now, I'm not going to work out with us together what exactly its mean and variance are as functions. So again, it'll have a mean vector it'll have a covariance vector. You can work these out in closed form. I will point you to places where you can see this worked out though, books where you can see this worked out. You can compute these with Gaussian facts. This is just taking this big joint Gaussian, this multivariate Gaussian of f of an x and f of x prime, and using known facts about what does the conditional within that look like. But it's going to be Gaussian. The thing we are going to do together is we're going to look at some demos. So in particular, we're going to now assume we actually have some data. That is to say, we have some observed inputs and some observed outputs. So that would be capital X and f of capital X. And we're going to ask, what is the conditional distribution? What is our probability of the unknowns given the observed data? What's the distribution over f of x prime given those observations at x? What is our knowledge about the testing data points given that we've actually seen the training data points? And we're going to, again, use this particular version of the squared exponential kernel with sigma equals 1. Okay, so now let's switch over. Really appreciate if anybody tells me if we're not successfully switching over. Hopefully we are. And so now we should be seeing the demo again. We should be going back to the demo. Sweet, thanks for the, the thumbs up. I appreciate it. Okay, so we're back on the demo. And what we're going to do now is we're going to assume we actually saw these 4 data points, that these were our observations, that this was the data we actually observed. We saw this air pollution value at this location. Okay, and so now what we're going to do is we're going to run Gaussian process regression on those points. And what do I mean by, say, running Gaussian process regression? I'm literally talking about exactly what we just did on the slide together. We're saying, hey, jointly, you can think of the joint distribution of the value of the Gaussian process at all of these different x locations, all of these different horizontal locations, together with the actual observations at these 4 points. So these black x's, these black crosses, those are actually the observed points. We actually know the x values and y values at those 4 points. And the goal here is to make a prediction away from those points. Now, in this particular case, because we generated the data ourselves, we can actually draw the true underlying function that generated this data. That's the blue dashed line. In general, you won't have access to that. You know, if I'm trying to predict the air pollution at places I've never seen it, I don't know the true underlying function. We happen to have access in this case because we simulated it, and that's nice for our understanding, but we wouldn't usually have that. What we would have is we would have everything else in this plot. We'd have the black x's, that's our observed data, so we totally know that. We have our predictions. So this green line that we're seeing, this solid green line, that's the mean of the Gaussian process away from the observations. And we're creating it just like we created our draws, or like we created our, our big prior Gaussian process before. We're saying, hey, what's the mean? In this case, it's non-trivial. It's not just 0 because it's conditioned on the data. And then finally, we have our uncertainties, our plus or minus 2 standard deviation interval. Now, before, this was pretty boring. When we were first generating things a priori, when we didn't have any data, the plus or minus 2 standard deviation interval was just plus or minus 2 everywhere. Now, because we've observed some data, it's not trivial. We're actually seeing that it differs depending on where we are in the space. And I just want to point out some things that might be considered useful about this. So one is when I'm really near my data points. Can anybody tell me, can you see my cursor? I just want to make sure that that's the case. Okay, great. Thank you. So, okay, so when we're near the data points, like over here or over here, basically around these first 3 data points, we see there's very little uncertainty. There's also very little uncertainty going between them because this is basically the only way we can smoothly and quickly go between these 2 points. However, when we get much farther away, so the second set of 2 data points are farther away from each other, now we have a lot of uncertainty because there's a good number of different ways that we could have gotten between these 2 points. And so it makes sense that our uncertainty would be larger as we get farther away from these data points. Now, something that hopefully we'll dig into shortly is, well, what does it mean to be far and what does it mean to be close? How do we decide what these scales are? But here, I'll say the scales are basically decided for us. And so we can say, hey, yeah, these 2 points are farther away. And so our uncertainty becomes higher as we get farther from points and as we get close to any particular point. You know, if we're really close to an air pollution sensor, feels like we're actually pretty certain about what the air pollution is. As we get really far from any air pollution sensor, then we're like, we don't maybe know as well what the air pollution is. And we'd like to express that we have uncertainty about it. And that's what we're getting with this ±2 standard deviation interval. This is really the heart of it. At this point, we have seen inference, what we expect from doing Gaussian process inference. And so I just want to pause for a second and just see if there are any questions before we go on and start talking about additional changes that we might make here. Things like, you know, what are the length scales we're seeing and things like that. Recognize that it might take a little time to put things in. Rho cannot be negative. Yes, so great observation. So for the particular choice that we made of the covariance function here, this squared exponential covariance function, I'm going to try to go back to the slides and look at that together. Right, so let's look at this, this kernel, this covariance function here at the bottom. For this particular choice, we're not letting the correlation be negative. We're only letting it be positive. I want to emphasize again, there are other things that you can do in Gaussian processes. So if you find that you're in a situation where you actually want to change some aspect of that, you might be able to. You could think about it. So you can choose a kernel so that you could have other behaviors. It's just for this particular kernel, again, known as the squared exponential kernel, that we're not allowing that behavior. Exactly. Cool, great. Okay, definitely feel free to keep asking questions as we go along. Again, I recognize that it might take a second to write these things up, and so don't worry about it if we're like a little bit farther ahead. We can always go back and talk about them again. Okay, so again, at this point, we've said, hey, what would it be like to generate, we have a method to generate these various possibly smooth curves. We now have a way to say, what do we know at other points, given that we've made observations at some points? What's our state of knowledge? Conditional on choosing a particular mean function and a particular covariance function, a particular kernel. These are choices that we've made, and they absolutely are going to influence what we conclude. And I just want to note that essentially we're really doing the same thing we did before. We just have a different distribution now, a different multivariate normal, because we had these observations. So in particular, to drive that home, let me try saying, hey, let's look at what we have conditional on this data, and note that we could again make random draws from the distribution of continuous functions, now just constrained by the observed data. So here, you know, previously in previous demos, we saw here's 3 draws of a random function. And in that case, it wasn't constrained because we didn't have any data yet. Now we have these 4 data points. And so we've constrained our random draws of the functions to go through the 4 data points. And here are just 3 draws from it. Because again, it's just a multivariate Gaussian is all that we're doing here. We're just making this multivariate Gaussian the same way we did before by having draws at many dense X values, at many dense input values. And so we can do the same thing here. It's just a different multivariate Gaussian. Okay, so this is meant to express our uncertainty and our best guess. Our best guess could be seen as this mean, this posterior mean. So these are the mean predictions, this solid green line. So that could be thought of as our best guess. And then our uncertainty around that is the ±2 standard deviation interval, conditional on the data that we've seen. And now we're going to dig a little bit more into some choices we've made and what are their implications. So let me go back to the slides again. Okay, so I said we're using the squared exponential kernel. That's the kernel that we just talked about, this, this covariance function on the previous slide. And one of the issues that came up kind of as we were talking through things is it seems like there's some notion of distance in the X values, and there's also some notion of distance in the Y values. And so what I'm going to do is I'm going to take literally the exact same squared exponential kernel from before. And in particular, by that, I mean, let me just go really briefly back here. I mean, I'm going to take this exact squared exponential kernel here, and I'm going to take sigma equal to 1 again. So that's, again, telling me the variance, how much I expect things to change in the Y value, how much variance I expect to have in the Y value a priori. I expect things to roughly, maybe not vary too much. You can think about, what do you think of a Gaussian with a variance of 1? And I'm going to see what happens if we had measured our data on a different scale. So now going back to the demo, so we should be seeing the demo again. So we saw, hey, if I had this data, it seemed like a pretty reasonable thing that I have a lot of uncertainty when I'm away from the data points, and I have less uncertainty when I'm near the data points. Notice that our Y values are measured from -3 to 3, and our X values are measured from roughly 0 to 3 and a little bit extra on either side. So the thing that I'm going to do, that I'm going to change now, is I'm going to say, well, what if we had measured our Y values on just a different scale? I mean, it's really common. If I was measuring something in meters, I might have measured it in centimeters or recorded in centimeters, or, my friend might have measured, her recordings in meters and mine in centimeters. It's very common to have things that are just a slightly different scale for whatever reason. And so I'm literally running the exact same Gaussian process regression that I did before. The only thing I've done is I've changed the scale of the Y values, but something's really different here. Can anybody tell me what changed between this plot and the previous plot? I'm still plotting all the same stuff. I'm plotting the exact same training data, just on a different scale, spotting the original function, which we happen to know it's the true function, plotting the mean predictions, and I'm still plotting the ±2 standard deviation interval. Awesome. Something has changed with the standard deviation interval. Exactly, yes. Great observation. We don't see it anymore. We don't see the standard deviation interval anymore. And I'm going to tell you, it's still there. It's just so tiny that you can't see it. And now let's talk through a little bit what could have possibly happened here. So the first thing to notice is if we go back to the original data, that standard deviation interval was always strictly less than -2 and 2. And so here you can imagine a situation where our uncertainty is still on the order of 4 or less, and we just couldn't see it because, man, the scale has totally changed. Let's think about what went wrong in our usage of the Gaussian process with squared exponential kernel, and then we'll talk about how we can change it, how we can fix it as well. Okay, going back to my slides. I'm alerting you when I go back and forth, so hopefully we all know. Okay, so let's talk about the assumptions. We said we were using this particular kernel. This particular kernel has a sigma equal to 1. So let's think about what we're saying about what we expect of the scale of f of x by using this. Remember, we're saying we assume that all of the data, the training data and the testing data, is coming from a Gaussian process with this kernel. That assumption is baked into our choice of mean and covariance. Like, there are assumptions about this process. And so let's ask ourselves, what is the range of values we're expecting from a particular x with this assumption? Feel free to answer this question at any point, but I'm going to start working through how we might answer it. The first thing to notice is that by assumption, we can find out what our variance is at a particular point by just choosing x and x prime to be the same point, because that's just going to be our covariance. So if x and x prime have the same value, just one particular value, x minus x prime is 0. Some great answers coming in the chat here. I'm going to keep talking just to get to them, but like doing great. X and X prime is 0. The X minus X prime is 0. So X of 0 is 1. And so the covariance for just this one particular value is sigma squared. Well, we said sigma is 1, and so the variance is 1. So we're basically saying our assumption a priori is that a particular X with 95% probability, we're going to be in a range of values that a Gaussian with mean 0 and variance 1 would take. And so the observation that we're seeing in the chat, and that I've just slightly rounded here, is that we know that a Gaussian with mean 0 and variance 1, a 95% interval for that is roughly negative 1.96 to 1.96, or just negative 2 to 2. The important point here is that a priori, if I'm making an assumption that my Gaussian has variance 1, I'm really expecting my values to not vary much outside of negative 2 to 2. I am assuming, if I make this assumption that my Gaussian has mean 0 and variance 1, that the vast majority of the time, it's going to be between negative 2 to 2. And so the problem we saw in our demo, going back to our demo, is that we are not allowing essentially the variance to be larger than that. As we get more data, I'll tell you a mathematical fact, and you can check this once you dig deeper into Gaussian processes yourself. The marginal variance can increase with the data. Another way to think about this is it's our uncertainty. As we get more data, in general, we expect to only become more certain than our original model. We should be learning something by getting more data. And so essentially our uncertainty can only decrease. Well, coming back to our demo, we said that our uncertainty could basically be only on the order of 4 to start with, something like negative 2 to 2. And then we got some more data and we can only become more certain. And so the size of our uncertainty interval could only be negative 2 to 2, or on the order of 4, and it can only become smaller. Well, this plot is on the order of negative 200 to 200. And so something that has vertical distribution or length, 4 is just going to be extremely small on this plot. So the main point is we shouldn't use something that says our uncertainty, that we only think the y's can vary on the order of 4 units, if we think that in fact they're going to vary on the order of hundreds of units. And that really is going to matter. It's going to change our uncertainty on the way out. Now, I'll tell you in a moment an automated way to deal with this. It's not something that you have to deal with by specifying these things in advance. You actually can automate this. But before I do, I'm going to tell you another thing that you should automate while you're automating it. Here's another problem that can go wrong. So what I'm going to do now is I'm going to go back to the original problem. So remember, here was our original problem. We had the x's on the order of 0 to 3. We had the y's on the order of negative 3 to 3. And so the thing we just said was, hey, if my y's are on a different scale, things can go really wrong. Now we're going to say what happens if our x's are on a different scale. So I'm going to do the same thing I did before. But now what I've done is my y's are on the scale of negative 3 to 3, but my x's are on the scale of 0 to 300 instead of 0 to 3. So what's going on here? Let's notice for a moment that, again, we have the exact same data. This is the data we generated together, these 4 data points, these x's. This really is a live demo. I didn't know what the data was going to look like until we did it all together. Now this is what it is. We have the original function, which we only happen to know because we generated the data. And generally, we don't know this original function. We're trying to infer it. And then we have our mean prediction. That's meant to be our best guess prediction. And you can see it's just almost immediately going to 0 away from the data points. And our uncertainty is almost immediately going to the prior uncertainty of negative 2 to 2 away from the data points. Now, we said earlier, when things were looking good, hey, it's desirable. As you get farther from the data, you have more uncertainty. But then it becomes a tough question of what does it mean to be far from the data? And here, by changing the scale of the x's, we're saying you get far from the data really quickly, and then things just revert to the prior. I will also be making all the code for this demo available on, well, I'll be making it available for sure on my website, and I'll share it with the ASA webinars folks, as is asked in the chat right now. And so I assume it will be available there as well, but definitely it will all be available for playing around with. And also all this is just in scikit-learn, and it's totally stuff that everybody should be able to run with standard packages. I'll just mention that. Okay, so this is a big problem too. I mean, this is almost saying we're learning nothing. It's saying that, you know, as soon as you get the tiniest bit away from the data, that we're just reverting to the prior. It's as though we don't know anything. So somehow this is an issue of X scale. So again, before I tell you an automated way to deal with this, I want to dig into why is it happening. So we said, as I transition back to the slides, we said the problem with Y was that we were assuming that the uncertainty to start with was on the order of 4 units in Y. And, you know, if truly that's not true, if we can actually take a much wider set of units in Y, then we have a problem. Here, it's not so obvious what we're assuming the length scale in X is, but let me dig a little bit deeper because it's actually happening that we're assuming the length scale at X here as well. You can think of what counts as close in X as being defined by what has a really large correlation and what has a really low correlation. So if we look at this particular kernel that we've chosen again, the squared exponential kernel, let's suppose that I have 2 X values that are distance 2 away from each other. So maybe X is 1 and X prime is 3. Well, if they have distance 2 from each other, then this squared exponential kernel evaluated where their distance is 2 and sigma is equal to 1 is about 0.14. That's telling me when 2 data points are distance 2 from each other, their correlation is already only 0.14. It's actually not too much correlation. When they have distance 3 away from each other, their correlation, which in this case is the same as their covariance, is only 0.011. These are almost independent random variables. And when their distance is 4 units from each other, their correlation is 0.0034. I mean, for all intents and purposes, these are just totally independent random variables. And so what we were seeing when we change the values on the x-axis, when we change them to be about 0 to 300, is we were saying, hey, all these points are just extremely far from each other. We're saying that basically points are independent as soon as you get 4 units away from each other. And so everything was just reverting to the prior. Definitely feel free if you have any questions or if you want to see any more about the demo, we can talk through any of that. But what I'd like to talk about next is how we might handle these things. Oh, please, is there?
I have a quick question. Could you please comment on, go back to the demo and comment about the fact that the function is changing at the observed points? I think it's an interesting discussion, right? That it's an exact interpolator.
Oh, yeah. Great. So let me see if this is the point you're getting at, but please push back if it's not. So we're seeing this thing, I mean, by construction. So we said there's no observation noise. So it has to be the case, just because of the way we defined it right now, that this function has to go through the data points. And so we're saying the point, this green function, that's our best guess function, has to go through the data points. And we have no uncertainty at the data points. So that's why we're seeing, again, the uncertainty intervals, they basically have 0 width around the data points. But conversely, as soon as we get 4 units away from this, we're saying that we're effectively independent from those points. And remember our prior, the thing we started with, when we were just generating functions, when we didn't have any data, it was this big gray slab that was -2 to 2. And I didn't draw it explicitly, but there was a mean of 0. And so that's what's happening in these regions here. Because we're saying the length scale is something on the order of 1 or 2 here, at which point data points are far away from each other. Here in this region, we're far from all the data points. 25 is way over 4 units from every observed data point. And so it's just going back to the assumptions we made without any data. It's saying, hey, the mean is 0, the variance is -2 to 2. I can't know anything else because I'm so far from every data point. Same thing in this big region here. If we're at 75 to 275, in this whole region, we're way over 4 units away from every data point. So we're saying, hey, we don't know anything about what's going on. We're just going to revert to our assumptions before we saw any data, which is to say a mean of 0 and a variance of -2 to 2. Now, we probably don't want this to happen in real life. We probably would like to say, hey, actually, the length scale here shouldn't be 1 if this data is observed from 0 to 300. The length scale in this direction shouldn't be 1 if the data is observed in some other direction. So we'd like to deal with that. Okay, let me repeat once more because there was a question in the chat. So remember when we were generating functions together, you could think of that as saying, what are the assumptions of this model before we've seen any data? And the assumptions of the model, we wrote them down explicitly, are that the mean is 0, and that our uncertainty around that mean for any particular point is essentially a Gaussian with standard deviation 1. And so we could make a 95% interval of -2 to 2. Now, the observation that we all just made together is that unless we set a different length scale, the default length scale here is about 1 or 2. That is to say, if I get more than 2 units away from another data point, I'm almost basically a totally independent data point, and it looks like there's no data nearby. And so I'm going to go back to assuming that things were like I had no data. And so that's exactly what we're seeing here. So if I'm at this data point here, and if I go 2 or even 4 units away from it, I am, by construction, by assumptions in the model, very far away from any data point. And so I'm going to revert to my assumptions when there were no data. That is to say, I'm going to revert to assuming that the mean is 0 and the standard deviation is 1, or my 95% interval is -2 to 2. And so if I don't want to do that, if I think that I actually should have a different length scale, my x's are on a different scale, I need to do something. I can't just use the model that we were using already. I have to make a different choice. Great. Thanks for the follow-up in the chat there. And same thing with the y's. We just saw that things can go wrong with the y's. If you just use the model that we've been using without thinking about it, you can make some bad assumptions about uncertainties. We're going to have to actually explicitly state what are our length scales and why. We can't just say, hey, they're 1 and expect it to work for everything. Okay. So how can we deal with this? First, I'm going to say something that's not going to fully work, and then I'm going to say something that people actually do in practice. Something that is very common to do, and is probably in general best practice before just about any machine learning or statistical algorithm, is to do some kind of normalization in the y's and the x's. That is to say, before you run any algorithm, you take your observed y values, you normalize them so that their empirical mean is 0 and their empirical standard deviation is 1, and you just remember the transformation you did so you can get back to it. And same thing with the x's. The normalization of y isn't a totally bad idea. It can be helpful. The normalization in x here is not going to solve this problem. Here's a little cartoon to illustrate. So if I normalize an x, that is to say, I make sure that the empirical mean of my observed x values is 0, and my empirical standard deviation is -1, 1. It can be the case that the length scale, that is to say, how quickly I expect these curves to go up and down, could still be very different. And so that's really the length scale we care about. Remember, essentially, we're saying when I have 2 different data points, how close do the x's need to be correlated, and how far do they need to be uncorrelated, to be effectively independent? And so that's telling me how quickly these curves go up and down in my function. And so this suggests normalization alone isn't going to help us. But here's something that can, and here's what people really do in practice, is they explicitly instantiate hyperparameters in a more general version of this kernel that encode these length scales. Okay, so here's a more general form of the squared exponential. So this is much like what we saw before, but there are a few little changes. So the first change is, hey, wait, we had sigma squared before. That hasn't changed. But what has changed is now we're going to learn it from data. So before we specified sigma squared, we said, hey, we're just going to set sigma squared to 1. We're seeing now that's not a good idea. We need to do something. Either something like normalizing y or just allowing the signal variance to be learned from data. So in this case, we don't need to normalize it. We can just learn the signal variance from data, and that should tell us about the size of y. Hopefully that's addressing the question that is also in the chat. Let me know if you have further follow-up questions on that. Okay, so the sigma squared, if we allow it to be learned from data, can potentially take care of that y issue, the scale of the y's. What about the scales of the x's? Well, what we essentially need to do is we need to explicitly introduce a length scale for the x. Now, in some sense, we were fooling ourselves before thinking we didn't have a parameter here. We did. You could think of it as the length scale was set equal to 1. And so we didn't see it, but it was really there. It was still working. Now we're explicitly instantiating this length scale. We're saying, hey, there actually is something that controls how far apart the x's are. You know, how quickly do we achieve a lack of correlation? And that's a length scale. Now, the other thing I want to point out that's happening here is while we were drawing things in one dimension, again, there could be multiple inputs. We could have latitude, we could have longitude, we could have time. These could all be inputs. And each of them might have their own length scale. You know, it might be that time is varying in hours, but the scale of latitude and longitude, well, I mean, it's just a completely different system, right? And so I might want a different length scale for each one of these, for each one of my inputs. And so here we have a different length scale for each input. I'm going to make a little note about nomenclature, and then we're going to actually see this in a demo, learning these different values. Sometimes you'll hear Gaussian processes called a non-parametric method. And so I'm just going to mention here that we might think of the parameters in general as the things that parameterize the distribution of the data. That if we knew the parameters, we could generate the data. And in this case, you could actually think of the parameters as that entire function f. And so sometimes we'll call models non-parametric because there's an infinite number of latent parameters. So it doesn't mean no parameters, it means an infinity of parameters. Hyperparameters, in turn, parameterize the distribution of the parameters. If we knew those, we could generate the parameters. That is to say, in this case, if we knew sigma squared and all of the length scales, then we could generate f according to that Gaussian distribution that we saw. And so we'll often talk about sigma squared and the length scales, the signal variance and the length scales as being hyperparameters. Okay, so here's the proposed algorithm. 1, fit a value for the hyperparameters using the data. And then 2, given those values, compute and report the mean and uncertainty intervals. And so let's go ahead and see that now on some data. Okay. So we're going to, again, draw our Gaussian process. You'll notice here that I have made a choice that is different from our original choice on the range here. So now I am drawing my data from a Gaussian process that actually has a signal standard deviation of 2 instead of 1. So this goes from -4 to 4 instead of -2 to 2. So I drew my latent function from the Gaussian process. I drew some data, that is to say, I specified some x values and I read off the y values according to the latent function. And now I have 10 data points here. And now what I'm going to do is before we ran our Gaussian process inference, assuming we knew the x length scale and assuming we knew the y length scale, essentially. And now I'm going to learn them instead. So this is what's going into my method. I'm only assuming I know the data points. I'm not assuming I know the x length scale and the y scale. I am assuming that I'm using a squared exponential kernel, but that's it. And then I'm going to fit that. So let's talk through what's going on in this graph. It's very similar to what we saw before, but it's a little bit different. So the similar thing is we still have our set of data. In this case, it's the 10 data points that we just generated together. Now, though, before we do our inference, before we do our predictions at other points, we're going to actually fit the parts of the kernel, in particular the signal variance, and in this case, it's a single length scale because it's a one-dimensional input. And so what we're seeing up here is I've written down the original kernel I used to generate the data. The algorithm doesn't have access to that. I'm just using that for comparison. And so in particular, the way to read this is that the signal standard deviation is 2 when I generated this data. And the single length scale is 0.3. And remember, another word for the squared exponential kernel is the RBF kernel, or the RBF covariance function. It happens that this code, which is default in scikit-learn, uses RBF. Okay, so now I can fit this kernel, and it learns with these data points a signal standard deviation of 2.09. That's pretty close to 2, not too bad. And it learns a length scale of 0.322. How could it possibly know these things? Well, if you think about it, the signal variance is telling us how things vary in the vertical direction. And there's certainly some information about that in the data points that we're observing, how much we might expect things to vary. And then the length scale is telling us how quickly things become uncorrelated in the horizontal direction. As we get farther out in the horizontal direction, how quickly things become uncorrelated in the vertical direction. And basically these points that are very near to each other. So I just uniformly at random chose the X in this case, but these points ended up near to each other. Well, they're telling us, hey, we can't vary too quickly because these wouldn't have had such close values otherwise. And so there's information about these length scales in both the X and Y directions in our data. And then once we've learned those, we can now use the exact same conditional Gaussian mathematics that we used before to say, hey, what's our best guess of the function value away from the data, and what's our uncertainty interval? And I'm plotting the original function again. And so we can see that the original function is going in there. So we have a question in the chat. What happened if we observed the X with equal distance? We'd have even more information. So in this case, if we observed the X's with equal distance, we'd have a lot more data points. I mean, assuming you had them about the same distance as here. And so we'd have even more information. We'd probably be able to nail down the length scale and the signal variance really well. We'd be very certain about those values. Also, we'd be a lot more certain about the function values in between data points. So if the data points are all very close to each other, especially on the relevant length scale on which things are changing, then in general, we're not going to have these huge amounts of uncertainty between data points. We're going to have a lot less uncertainty. Like, for instance, these data points are very close to each other, and so we're very certain of the function values between them. Awesome. Okay. So this is really what you're going to do in practice. You're going to be choosing these hyperparameters. Great question. What hyperparameters are being put on the length scale and the signal variance so that these parameters can be learned from data? So you are clearly familiar with Bayesian inference, and this would be a really natural thing to do, is to put a prior itself on the hyperparameters and then use that to learn all of this. And if I did that, I would not be able to do things as quickly in this live demo as I have, because that would take some, Markov chain Monte Carlo approximation or something like that. What I've actually done here, and what's often the default in various packages, and is certainly the default in this software package, is to learn the hyperparameters via maximum likelihood. And so you can think of this as type 2 maximum likelihood. Yes, this is exactly an empirical Bayes approach. So we're still taking a Bayesian approach on the parameters in the middle. You can think of, again, the parameters as being this F function, but then we're taking a maximum likelihood approach on the hyperparameters. And that entails everything that it usually does with empirical Bayes. That is to say, a really important thing that we should be thinking about is, what uncertainty are we capturing? The uncertainty that we're seeing here is the uncertainty conditional on these being the correct hyperparameters. We're not capturing the uncertainty that is inherent in choosing the hyperparameters in the first place. Also, as with any Bayesian method, we're capturing the uncertainty in using this model to begin with. We're not capturing the uncertainty in whether this is a misspecified model or something like that. And that's just true of any uncertainty that we would get for Bayesian inference, and it's true of the uncertainty here. And so absolutely, this is an important thing to be aware of. Okay, I see that we're nearing the end of our time together. And so what I'd like to do is just wrap up what we've done today, talk about some directions for future exploration, if you have time on your own, and point you to some resources. So let me go ahead and do that. Let me just go ahead a bit here. Okay, here we are. Okay, so just to recap, today we started with how we might take a Bayesian approach to learning functions, these smooth, nonlinear functions. We started off with a model, what we might expect functions to look like, if we didn't have any data, in particular a popular version using a squared exponential kernel. We talked about a length scale hyperparameter and why it's so important in each x value. We talked about a signal variance hyperparameter and why it's so important in the y values. What we didn't have time for, but is also important, is an observation noise variance. So there's absolutely a version of this where you can allow observation noise at the individual observations. We assume that we observed that function perfectly, but often that won't be the case. And there is an extension of the squared exponential kernel that allows that. And that's also, again, really standard in standard software packages. So that's something to be aware of as well. We talked about Gaussian process inference, in particular, how we're just going to use basic multivariate Gaussian calculus to predict at points away from the observed points and get uncertainty quantification. We talked about some limitations, but there are other ones we didn't talk about yet, and I want to just highlight. One is extrapolation. I think something you should be aware of, not just for Gaussian processes, but literally everything you ever do in life that is extrapolation, is that when you are extrapolating, you are usually using the assumptions of the method. So in Gaussian processes, you want to think about what those assumptions are. Usually you're doing something like defaulting again to this knowledge that if you didn't have any observed data. But really, no matter what you're doing in extrapolation, you're using those assumptions, and it's worthwhile thinking through what that is. Something we also didn't talk about, I mentioned briefly at the beginning that GPs tend to be used for low dimensional inputs. So again, things like latitude, longitude, time. 3 dimensions, that's totally low dimensional. But if I have a situation where I'm trying to do hyperparameter tuning for my complex deep learning algorithm in machine learning, and I have 100 different hyperparameters, now I start to have some issues. And those issues often arise because GPs, as we talked about, really depend on the distance between points. And in high dimensions, all points are far from each other. And so you get this issue of you sort of revert to this prior behavior when you don't have any data. We haven't had time to go deeply into this, but it's something to be aware of. And I think a great question or set of questions that came up at the end were this, what uncertainty are we quantifying? We always need to be thinking about, in any method that provides uncertainty quantification, the difference between uncertainty quantification as a term of art that responds to and discusses some particular form of uncertainty, and uncertainty quantification as we'd like to use it colloquially. We'd like to say, hey, here are all the ways that I'm uncertain, and here's some quantification of that. But whenever we use any particular statistical or machine learning method, it's going to be getting some particular aspect of that. And this is no exception. And so I think that's just always worth thinking about. And I really appreciated that we have a bit of discussion around that point. Okay, so again, my hope today was that we learned a little bit about how Gaussian processes work. And so hopefully it's clearer what things might go wrong when you use them in practice. When you see some weird plot that looks weird, you can say, oh, I know what happened. I wasn't learning my length scale, or I wasn't learning my signal variance. And so here's something I can go back. I can make sure that I'm actually learning these hyperparameters, that I make sure that I'm using the default software package in the right way and make these choices. And then I'm just going to conclude by pointing you to various resources. There's an amazing book, even though it's a bit of an older book at this point, it's just still, I think, incredibly useful, this Gaussian Processes for Machine Learning book. All the books that I'm pointing out here are all free online. There's an awesome book about surrogate modeling in particular that's focused on surrogate modeling. And so this is a much more recent book by Bobby Gramercy, also goes over some Gaussian processes stuff along the way. Roman Garnett has a book on Bayesian optimization. So often people don't just model smooth functions with Gaussian processes, they use that to optimize over this space. Maybe I want to choose the best rocket booster lift. Maybe I want to choose the best performance of my deep learning algorithm. And so you can do that with Bayesian optimization. Again, an extremely recent book on this topic. There is tons of default software, and so there's no need to code your own, although you absolutely can, but there's a lot of options out there. And again, I'll be sharing my slides and my code. Thank you so much. Thank you for being so awesomely involved in today's tutorial and answering all my questions. Really appreciate it.
Wow, Tamara, thank you so much. Thanks a lot for such an awesome introduction to Gaussian process. If I may, I would like to hear your opinion about the situation when we put hyperpriors to the parameters in the covariance function, and which tool do you usually use if you use MCMC or, I don't know, INLA? I don't know. I would like to hear your opinion about this.
Yeah, it's interesting. So I think they're actually, there's a real trade-off. So basically, there are substantial inferential benefits from putting on these hyperpriors. Like you are quantifying more uncertainty that's out there. You're capturing that we often don't know exactly what these parameters are. And the real trade-off is, I think, in running time. And maybe this is part my background. I tend to lean towards MCMC. I use MCMC when I'm doing something over the hyperpriors. I will freely admit that in part that's because I'm not as familiar with INLA. So maybe INLA is the way to go on this. And so I don't want to say that I come down really strongly one way or the other. But certainly between MCMC and hyper parameters and using type 2 maximum likelihood, I find a pretty substantial difference in terms of running time often. And so one option too can be, if you're just trying things out and like getting a sense of what's going on with your data, you could start by doing something like a default package with type 2 maximum likelihood. And then when you get to the point where you really start caring about those uncertainties and you really, it really matters to you that you're capturing more and more of the uncertainties, maybe you invest in a longer Markov chain Monte Carlo run or something like that. I think that could be a potential trade-off in practice.
Mm-hmm. You started with your example with the temperature measurements across the ocean. Usually that data set is huge, like the number of points that you observe is huge. So could you briefly talk about the limitations of Gaussian processes when you have these high dimensional data sets?
Yeah. So this is super classical and a great point to bring up. So it's well known that basically when we do this conditioning that we talked about, that we're saying, okay, now that we've observed this data, we'd like to predict at other data points. When we do this sort of Gaussian methodology, we essentially end up having to invert a matrix that's on the order of number of data points by number of data points. And so if I have a number of data points, in particular that exceeds 10,000, that matrix inversion can become very expensive. And so this is just a well-known challenge with Gaussian processes. I'll also say it's also why Gaussian processes tend to be most widely used when the data that we gather is very sparse and very expensive, because then we tend to have, one, fewer data points to begin with, but two, we're willing to spend a lot of computation time for those data points because that's not the bottleneck. The bottleneck is, having gone out into the ocean and placed buoys and stuff like that. And so, but that being said, super active area of research, and there's a ton of research in speeding up Gaussian processes beyond 10,000 by 10,000 data points. And I think because there's so many different ways to approximate this, it starts to be useful to think about what assumptions are remaining and what approximations would be appropriate for those assumptions. But I will say that there's also a lot of modern day software packages that have at least some kind of approximation to a Gaussian process, that is to say, a really fast approximation to speed up these kinds of computations built in. And so I think for the new user, that's probably the way to go, is using one of these default software packages and their speedy way or their speedy approximation for Gaussian processes.
Wonderful. One last question from the Q&A, I promise. Which of the resources you mentioned is the best place to start for someone new to GPs?
Great question. My personal feeling is I really like this Rasmussen and Williams book. Like, I would just read chapter 1 and 2 in particular. There's, by the way, I should mention, there's a lot of chapters in this book, and you should not feel like you need to master all of the chapters. I think 1 and 2 really get like the absolute heart of what's going on. And so I think if you just got to chapters 1 and 2 in this book, you'd have actually a really good sense of the main ideas of what's going on. And then if you wanted to go a little bit farther, thinking about things like covariance functions and stuff like that, you might look into chapters 4 and 5, but chapters 1 and 2, I think, will get you started with the math and the heart of things.
Okay, I have just posted on the chat again the link to our website of SIRS. Tamara will kindly make the slides available, and the recording will be available there as well. So again, thank you so much for a very nice introduction to Gaussian processes. Those of you who are still in the audience, stay tuned for our next edition of the webinar. We are organizing it, and hopefully soon we will have an announcement. Take care, and see you all soon. Thank you.
Thank you so much. Really appreciate it.